Be live? Yep.
Okay.
Okay, welcome everyone. So we start our official workshop talks now. Today we have with us Dr. Xaq Pitkow. He's a PI and an assistant professor at the Department of Neuroscience in Baylor College of Medicine and the Department of Electrical and Computer Engineering at Rice University. Some of you might have already heard his previous talk at our ICAWE colloquium, and I'm super happy to see what else he has to present today. And Xaq, please take it over.
All right, thank you, Ashima, for the invitation, and for those of you for returning, and for the new faces there, welcome. All right, so I'm going to tell you about mind reading by math, and this is a project that we've been working on that uses reinforcement learning, and in some cases deep reinforcement learning, to go in the backwards direction. So let's talk about it. This is joint work with a number of colleagues of mine. Paul Schrader is a PI in Minnesota, and the lead on this work has been Zhengwei Wu and also Minhei Quan. And Saurabh Daptardar and Yizhou Chen have also been deeply involved in this, as well as a whole bunch of other people, and thanks to the funding sources for making it possible. So the motivation here is that I'm a neuroscientist, so I try to study the brain. How does the brain work? And conventionally in neuroscience, when you're thinking about systems neuroscience, you relate brain activity to something observable, like the sensory input. In visual neuroscience, for example, you measure the scene, the image or the movie, and you compare that to the neurons and you figure out that relationship. Or in motor neuroscience, you measure the neurons and you measure the muscles. And so then you can figure out that relationship, and that tells you a lot about the brain computation. But there's a lot in the middle between the sensory and the motor. Cognition, for example. And so you can still measure the activity of the brain, but what are you going to compare it to? So that's what we try to do here. We try to infer what the thoughts of an animal are from what it does. And this is built on the framework of partially observable Markov decision problems. And so I'm going to lay out the framework here for you. You start with an assumption about the world, namely that the world is Markovian, which means that the state of the world at some time depends only on, the transitions to the next state depend only on the current state. And you can think that if you do this in continuous time, the changes in the world depend only on the current state. Okay, that is a first order Markov process. And physics is fundamentally Markovian in this sense, although at the coarseness that we observe it, there might be a lot of things that hide some history in there. So it looks like there's a greater history dependence. But if you have the right variables, then you'll get a world that's Markovian. And that simplifies the math. Now, the world as it stands is actually not observable. It is latent. And so what we get about the world, or what an animal gets, is sensory observations, which are partial observations of the world. And it uses those to construct an estimate or belief about the world, perhaps more than just a point estimate, also including uncertainty, and uses those beliefs it updates those beliefs based on its mental model of the world and all those new observations. Now, because everything is stochastic, that makes things a little complicated. So you have single events in the world that could correspond to many possible events in the brain, many observations in the brain. And conversely, one activity pattern in the brain can correspond to many possible events, which means that neural computation, what the brain is trying to do to interpret the world, is inevitably statistical, which provides us with some nice mathematical predictions. So if we go back here, we can use the language of probability theory to anticipate what the beliefs are when you observe these things about a world that you make assumptions about. So the Markov property says, as I was mentioning before, that the probability of the world state at some time t, which is technically potentially a function of all previous states of history from 1 up to just before, is actually simplified into depending only on the previous time state. And we imagine that the observations are dependent on the current world state. Now, it may be that they're dependent on a richer aspect of the state, but this is an instantaneous observation. And it can be integrated together. A whole sequence of observations can be integrated to give an estimate of the current state based on the entire history. This is the posterior. And we can write that in a recursive formula using the hidden Markov model equations, which say that whatever you thought yesterday, you can anticipate based on your knowledge of the future how that will spread out over time. So if you imagine that X was going through some random walk and you thought that X was here, for each possible X that you might have had, it could move a little bit more in some new direction according to this transition probability. So you say, whatever I started off with and I wasn't sure, all of those trajectories are going to spread out further. And that's going to leave you with the sum term. If you add up over all the histories, this is your prediction about the future, the next step before you've made any new observations. And so we can consider that to be a prior. And then we multiply it by a likelihood, which is the probability of the observation from that state. And then together, this should be a proportionality. You can normalize that and get a posterior. The prior times the likelihood is the posterior. Okay, and please feel free to interrupt me if you have any questions or requests for clarification. Okay, what about action? The reason for having a brain is to be able to act in the world, to do things based on your beliefs. If it were a dead end, you believe something but then cannot act, there's little incentive for evolution to learn a brain because it doesn't have any output that affects you. But the actions are based on your mental state. And in particular, we model them here as being based on your belief. Okay, so this little trellis diagram is the core of a partially observable Markov decision process. And so we imagine that you're bouncing back and forth between the world and belief mediated by observations and actions. We'd like to understand the consequences of this process for the actions so that we can figure out what we are not able to observe. For the animal, it's not able to observe the world, but for us, we are not able to observe the beliefs. We must only infer the beliefs. Now, what do we know about the world and the brain in particular? Well, we make an assumption that the brain is matched to the world. And this has been very productive as a hypothesis for a long time, giving you principles of optimality, saying this is as well as you can do. And the question is, what if the agent is not optimal? What if the agent is wrong about something, the animal or the robot or whoever is doing these actions? If the animal is wrong, that means that this optimality principle can't hold. But what are we left with then? We're left with this trouble that it's like dividing the world into bananas and not bananas. There's a lot more ways to be not bananas than there are to be bananas. A lot more ways to be wrong than to be right. There's only one right answer. And so what guidance can we get about understanding what an agent is doing if it's not optimal? So here we make the assumption that it is wrong, but rational. And by rational, I mean that it's doing the wrong things, but for its own right reasons. It's acting self-consistently in its own interest. And that gives us some guidance about what we expect to see. Now, how do we tell what that is, that wrong thing? Here, I'm going to do a little audience interactive demo, and I apologize for those of you who have played this game already. Let's see if you get it right this time. I would like to request that you all turn on your cameras for a moment, and we'll play this game. If you've played this game before, you can leave your camera off so I don't get distracted by people who already magically know this. But if you haven't, or if you want to play anyway, thanks for turning your camera on. Okay, so here's the game. You are driving down the highway in your car, and you're in the right lane, and you want to switch to the left lane to move around somebody who's in front of you. They're going too slow, you want to go faster. So you're going to hold onto your steering wheel, and you're going to move your steering wheel how you would move it to change change lanes in the car. Okay? And you're going to close your eyes and imagine what you're doing here. Ready? On the count of 3, change lanes. 1, 2, 3. Change lanes. Okay. Everybody's dead. At least what I saw. Maybe some of you got this right. It's a little hard to tell with this many faces, but what I saw you do was to turn to the left and then straighten out. Is that what you did? Anybody do something other than that? No? So what does that do to the car? It turns the car, and now you're going diagonally, and you straighten out, and you're like, okay, I'm going to keep going diagonally. Now that will leave your lane, but it's going to keep leaving your lane. You're going to cross into the opposing traffic and get a head-on collision. So you're all dead. What do you have to do? You have to steer back, right? You have to steer to the left and then steer back to the right to go parallel to the road. You have to make an S turn. But nobody does that. Why don't we do that? Why don't we know that for those of you who drive with any frequency at all and change lanes? How come you don't know that you have to turn back into your lane? You can unmute and make a guess.
Because we get feedback?
Yeah, exactly. We give feedback. Thank you, Michael. We don't drive, most of us, with our eyes closed. We drive with our eyes open, and when we see things that are happening, we correct them. So here we revealed your internal model by requiring you to make a prediction without feedback. This exposed your assumptions about the world. And so that is what we try to do in these experiments. We try to reveal an animal's or an agent's mental model by taking away the sensory evidence and requiring predictions. So this is this is our little mental model of that trellis diagram that we saw before, just depicted in a different way. Here's the monkey's head, and the monkey gets some observations about the world. And those observations influence, influence the, I have a chat here, because we drive without thinking, yes. Those observations influence the beliefs that you're constantly updating according to your internal model. And that arrow here is what you do when you don't have feedback. Those beliefs get evaluated by some value function we call Q. And that Q function can lead to an action. And that action then affects the world state, which can give you new observations and hopefully some rewards. The actions may also incur some costs. Now, this is our mental model of the animal, and this is, in a sense, the optimal thing to do under some assumptions about the structure of the world, which are pretty natural. So you would say, well, okay, now you're making an optimality assumption. Yes. But we're going to imagine measuring that behavior and imagining that it is correct, but under the wrong parameters about the task, or potentially the wrong structure about the task. So all of this depends on some parameters, which is the assumptions for how the world evolves. And the assumption, or not the assumption, the subjective values of rewards and actions. So all of those are parameters that we don't know. And we're going to measure those parameters or estimate those parameters by computing the probability of the data that we observe under each possible model. How do we do this? Well, we start with this POMDP, which is grounded in a Markov decision process. And a Markov decision process, without the PA, the MDP, is a sequential decision-making process where you're trying to maximize your rewards. Now, the difference here is that the current world state in an MDP is observable. It's the future that is unknown. And what you need to evaluate or to calculate the what to do is you need to construct a model. You need to know the transition probabilities. You need to know the subjective rewards and costs, and the policy, which is what you do in those different conditions, which together can be integrated to give you a value, which is intimately tied to the policy. If you're doing things optimally, you're going to try to maximize your value, which is your long-term expected reward. Now, when things are partially observable, making it a POMDP, now the current world state is uncertain because you have those partial observations, and the current uncertainty is known. So it's you are uncertain, but you know how uncertain you are because you can construct a posterior of it. So that is, in the sense, fully observable in the posterior. Now, of course, the future is still unknown, but now your future uncertainty is unknown, right? So that's this is equivalent to a belief MDP, a fully observed MDP, where the state is not the world state, but your state of knowledge, your belief state. So you can express the same stuff, but just in terms of a new set of probabilities, instead of the world transitions, these are your belief transitions. Instead of the rewards, it's your expected rewards. The policy is still the policy, but now it's a function of the belief state. So what we do here is we define this new problem setting called inverse rational control, where we assume that agents are rational, meaning they have the wrong assumptions. And we infer which internal model would explain those observed actions that we see under the observations that we see. So we're watching the animal do its thing, and we're using those observations, and the animal is making its own observations and taking actions, and we see all that to estimate its latent belief dynamics over time and compute what assumptions it was making that justify or rationalize those actions. Now, there are other things that are related to this in this family. Inverse optimal control infers the dynamics for given rewards. Inverse reinforcement learning infers the rewards given the dynamics, and inverse rational control infers both. Okay, so we have that trellis diagram that we looked at before. Now, for an agent, the empty circles are the latent variables. And so for the agent, the world is unobservable. But for us as scientists, we take the same trellis and we do observe the world, and we observe its actions and sensory observations, but we don't observe its beliefs. And so that's what we have to, that's the variant on the problem that we have to assume. So we do this by observing the actions and observations and estimating the parameters, which include parameters for the dynamics, for the uncertainties, for the rewards, and for the action costs. We infer the latent beliefs and then marginalize over those latents that we see. And technically, we use that Markov structure to decompose this probability and then use the expectation maximization algorithm with an analytic gradient. So let me just elaborate a little bit more on how we decompose that, that Markov process. Here we have the probability of all the stuff that we get to observe plus some stuff we don't get to observe. So we have to do the marginalization of the belief, which we do by EM. But the complete probability here, which includes all of that as if we observed everything, or just the probability of all, given theta and phi, which are respectively the agent's parameters theta and the experiment parameters phi, which the agent doesn't know but we do, we can factorize this using the Markov assumption. And so we can just trace this down. Let's say what you want to do is compute the belief at the probability of the belief at time t, which depends on the belief at the previous time according to the model, and it depends on the previous observations. So here b at t+1 depends on b of t, o at t+1, the most recent observations, and also on the actions, which we assume are known through the belief state. Then, okay, what was the probability of O? Well, that was a function of, that was a probability depending on S, according to the subjective model of observations. The belief transition, the belief state, depend on the assumed transitions T through the, given the previous state and the previous action. And finally, the action is a function of the previous belief. So we just trace back through this trellis, multiplying the probabilities of transitioning from one state to another over time. And that allows us to decompose this. If, as we are going to do, we take a log of this thing, this just turns into a sum of logs for each term, okay? And as long as we can compute these, given some assumptions about the world, then we're in good shape. All of this depends on having a good update for the beliefs under the model. The actual, sorry, I misspoke earlier, the actual observations that you get depend on what really happens in phi. And so the full likelihood depends on the experimental parameters. But the way that they are treated or handled by the agent, which is to update the beliefs, that depends on its internal assumptions. And when in the end you average over all the stuff that you can't see, some of these probabilities go away because they don't depend on the agent's model. They only depend on the ground truth, which we know, and so we're not optimizing over it. So given that framework, how do we actually find the model and the probabilities? We create a task family of problems. And within that task family, we use the policy that we parameterize it by some theta, and we solve for all policies within that family, use that to compute a likelihood over tasks, and maximize that likelihood to find the best interpretation of the observed animal behavior as rational. Now, a couple decisions have to be made here, and I'll tell you about two of them. One is, how do we represent beliefs? Well, option one is to discretize the probability distribution, and that can work for sort of small problems. And here we're dealing with small problems because we're in the realm of neuroscience rather than robotics. So this is feasible in some cases. Option two, you might want to use a parametric family, and we do this also, for example, a Kalman filter, and I'll show you an example of when we do that as well. And then for more complicated tasks, we'll have to do something else that we haven't done before, which is to learn a representation or use a more sophisticated representation, which poses its own challenges of how do you interpret it. One of the advantages of options 1 and 2 is that it gives us this explainability to the latent state that we otherwise wouldn't have. So if the representation is something learned and complicated, how do we interpret that? Now, the other thing we have to do is to solve for the policies. And there we have we've taken two different approaches for two different applications. You can either use value iteration to solve for a value function explicitly under a stochastic policy, and that policy is dependent on, is like a softmax over the value function. So that's one option, and this is the Bellman equation that you get for expressing the value function in terms of the instant reward plus the average over future states and actions under the policy and under the transitions. Or option 2, oh, and sorry, that's true. So what I showed you here is for the world state, and this is the conventional stochastic policy value. But here we're doing it for the belief state. So all the quantities are the expected values under the observation model. Or option 2, you can use something like an actor-critic method or something else that directly gets at the policy. But the point is you have to be able to write down to compute that likelihood, the probability of taking actions given different beliefs. And so as long as you can construct that thing, then you can use our method, which will then propagate gradients through and allow you to take these likelihood terms. So in some cases, we use a neural network for the policy because the interpretable part that we focus on is the beliefs and the parameters. Okay, so let me briefly tell you about a couple of applications that we've done with this. And this is very much ongoing work, which is really exciting. And we're now recording from brains of animals doing different games and trying to understand how they think and why. So one of the examples is we have an animal that is playing a foraging game where it has two feeder boxes, and it can go back and forth between the feeder boxes at some cost and reach up and grab some food from the boxes at opportune times, but it only gets partial observations about when the food is available. And so it has to make a mental model to predict what is the best thing to do. And we can observe based on when it reaches for the food and when it switches sides of this box, what it's thinking about the dynamics and values of that task. So we at the same time have recordings from the animal's brain, which are transmitted wirelessly to the experimenter, as well as eye tracking to know where the animal is looking. So we can relate all of these things to brain activity. And for that task, we can write down, so to demonstrate proof of principle, we can write down the different task parameters and beliefs about this and optimize it and show that for a case where we know the ground truth in simulation, we can recover what the agent is actually thinking, the assumptions of the model. And we're still working on doing this for the real monkeys, but we've been able to estimate things that look very much like subjective probabilities that relate to the neural activity even better than the true probabilities in this task. It's not a really strong effect yet, and we're still updating this, but it's very exciting time for applying this stuff. This is what the dynamic belief estimates look like. And it's interesting here, you have a probability over what beliefs the animal has, which is a probability over a probability. And you can see the discretization here that we used to make this feasible. The estimates that we get nicely match the true beliefs of the simulated agent. And when we go to the monkey, we don't know what it's actually thinking. So we need to trust this tool and know where it can go wrong. Another task that we're doing with the monkeys is called the firefly task, where the animal has to steer in virtual reality to a target that appears transiently and then disappears. And the ground plane texture also is only transient, so there are no landmarks to rely on, but only optic flow cues. So we have monkeys that have been playing this game for many, many hours, many, many trials, and they do a good job. And we have humans doing that too. In fact, this is the previous one is a collaboration with Valentine Dragoy. This is a collaboration with Dora Angelaki, and she's got the monkeys at the same time stuck in a motion capture chair, where as you move around, or you can do this with humans too, I've played this game, it's fun. As you move the joystick, your world physically moves at the same time. So you can evaluate the relative importance for your estimates of the visual input versus the vestibular input in your inner ear. So here's an example of a rewarded trajectory and an unrewarded trajectory. And we use belief dynamics to estimate what the animal thinks, where the animal thinks it is, which it should stop on the target, and compare that to the actions that it takes to figure out how its uncertainty grows over time, what it thinks about the gain, and the relative cost of moving in this world. And so we're able to recover in simulation what these dynamics are, and we're currently, so the horizontal axis is the true agent parameter in this simulation, the vertical is the estimate, and so this model is able to recover with good fidelity what is actually happening. And we're applying this right now, but we also have analyses of human data which are looking at, which can differentiate between different mental models. For example, we see that humans tend to undershoot, they tend to overshoot for close by targets. And two possible reasons for that is that you're not integrating the optic flow well, or that you're just underestimating the optic flow at every time. So there's the slow speed prior model, or the leaky integrator model, that has been the dominant one proposed in the literature. at least before we wrote this paper. And it turns out, so this is where you believe you are, and this can explain potentially where you stop when you're playing the game. And if the model stops at a time that is consistent with these different assumptions, you can see which one of them better reproduce what humans actually do. And it turns out that the leaky integrator model doesn't have the same dependence on the target distance that the slow speed prior model does. And so we can actually, basically you would just keep overshooting as you go on, because in the leaky integrator model, you forget that you've already moved anywhere. So in some sense, if you think about it more, you can kind of rule out that this is not a great model for traveling a great distance, because you've moved. You don't forget that you've moved in the beginning. But anyway, it's more consistent with the human data this way. So these are the kind of things that we're doing to apply this. And so just to close with a couple of discussion points real quick, because I know I'm over time. The existing methods for data-driven dimensionality reduction, which you might use in the brain, they scale in complexity nicely, but they lack interpretability. These include like latent variable methods and deep learning networks. We, in contrast in this, we take some of those tools, but we use model-based structure. We use a cognitive model to provide interpretations. And so this is what we could call scientific machine learning or explainable AI. And so I think that this is a powerful class of tools that we can use to understand lots of things, ranging from whether it's reading the mind of a person or an animal based on their actions, or trying to understand algorithms of a robot and seeing what kind of assumptions it might be making that are wrong. I actually was contacted recently by a surgeon who was interested in figuring out why other surgeons are making mistakes and trying to make a mental model for what assumptions they have that are wrong so that they could fix the surgery errors before they happen. So that's an interesting approach. So in conclusion, we have this inverse rational control framework to read off how an agent thinks based on how it senses and acts. And we are in the process of applying this to neuroscience stuff to see evidence of latent beliefs in the neural activity that we're able to record. And so, just, of course, there should be the necessary warning. Be careful when you're doing mind reading. This is a dangerous tool. And AI in general is a very powerful and scary thing. So we should all be aware of the ethical implications of it. And finally, just thank again my collaborators on this, who have been outstanding to work with. And Zhongwei is actually on the job market now. So good luck, Zhongwei. She's amazing. And with that, I'll thank you also, and can stop sharing my screen.
Thank you.
Now we have some questions. I'm happy to answer them.
So you can raise your hand so that we can have the questions queuing up. So the first question is from Vivian.
Yeah, first of all, thanks a lot for the really cool and interesting talk. I actually have two questions. One is a small question. So you assume that the agents have actually a stochastic policy, if I got that right. But then in your experiments, you can only observe the actions that were actually taken by the animal. I don't know if I just missed that, but how do you address this point in your model that you don't have access to the actual policy parameters or probabilities for the actions?
So great question. There are a couple of different ways to do this. So you can either assume that you have a stochastic policy, or that there are additional sources of stochasticity that lead to uncertain actions for us from our point of view. So for example, the agent makes some sensory observations that we see, but there's also noise in the brain and noise in the sensors. And we don't see those. So that can by itself lead to uncertainty. And you might have uncertainty in the belief transitions as well. All of those would be folded into, they're all latent, so we can't distinguish them very readily. They all get folded into a stochastic policy. But that being said, a stochastic policy is something that you can have a probability distribution on, right? You just have a probability of different actions, and you say, what was the most probable state that generated that particular action. And when you observe multiple trials of something, then you can constrain what that was. And in the end, if you have just a single trial of something and you have the model, now you're not going to know definitively what the belief was. You'll have a distribution over it. So that's why we have a posterior over posteriors.
Okay, thanks a lot. And then I would have a more open-ended question, but if someone else wants to ask, you can. Someone else.
Oh, let's hear the big question, and I think we have still 7 minutes. So.
Okay, so yeah, you talked about applying this to the real world or figuring out why surgeons make mistakes or animals act the way they do. But did you also try to apply this actually to reinforcement learning agents to figure out why they, for example, don't learn the policies we want them to learn?
We haven't done that yet, and I think that that's a neat idea. In particular, you could find out some classes of errors that are, maybe there are certain particular challenges that learning is slow to learn, and some other features that learning is fast to learn. And you could discover that potentially by looking at applying inverse rational control to, or even just inverse reinforcement learning. I guess inverse rational control would be better in this sense, to an RL agent. I think it's a great idea. The challenge is that it needs to be model-based. That's the way that this whole thing is founded. So if that means that it's going to impose that model on any data that it sees and interpret any error that it sees as an error in the model, as attributable to the model. So that may not be the case, and so you may be mistaken and you're kind of shoehorning things down, but that's the trade-off, right? You impose more structure and you get out more interpretability in terms of that structure.
Right. Yeah, thank you.
Sure, thank you.
Michael?
There are two Michaels. Michael Marino, I guess?
Michael Marino.
Yeah, I guess it's this Michael. Yeah, so I'm not sure if this is just kind of, I only have a really high level view of what you're doing here, but so the way that there seems to be this implicit assumption about the rationality of actors that I find pretty interesting, and a kind of
an explicit assumption.
Yeah, an explicit
an
explicit assumption of rationality, which kind of it kind of reminds me of this this assumption in economics that's beginning to be questioned, where for a long time economic theories were based on this rational consumer assumption, and they're now contemporary economists are beginning to see that the assumption that people make decisions based on rationality is kind of a poorly formed assumption. Do you kind of have you thought about this at all, or how kind of the irrational nature of our behavior could be sort of missing inside of this model?
Yeah, absolutely. So there's a couple ideas that are related to this. One of them is like the Kahneman and Tversky stuff, where there's probability distortions. But there's also work by Ed Vool and others that show that those distortions can actually be understood as rational with different kinds of constraints, whether it's bounded resources or the wrong assumptions about the world. So I think the rational that you're talking about is rational in the sense of optimal, whereas you might still be rational but suboptimal, meaning that you're making mistakes that can be explained. So they're, I would say, lawful, but not optimal. And that's the sense in which we are using rational. Rational, like rationalizing, like, oh, I did that because such and such. You might not have actually done it for that reason, but that's what you rationalize. You make it seem like it's the right thing to do. And that's kind of the flavor that we're trying to impose here. The other thread is bounded rationality. So it might be that you are in fact optimal, but you have constraints. Like in your brain, you're only able to think at a given speed. You're only able to consider certain sets of options, and you can interpret that in terms of one of these, maybe a part of an external model that is bounded here. Like you have subjective costs or dynamics that are different from the real world. Or I think another interesting thread that we're pursuing here is computational constraints. So you actually pay a cost for thinking, not just a cost for taking an action. And so that can lead you to having a different kind of solution, which may explain some other data.
Okay, I got it. Thank you for that.
Sure.
So I have a question, like a follow-up to what Michael asked. Can we model heuristics, for example? So if we can model rational behavior, subjects or humans usually take shortcuts to decisions. Can we model these heuristics as well?
You sure can. What you need is to be able to construct a probability over the actions given the observations. If you can do that, you can use this general framework. It may lose, and then you might have a family of heuristics, and it might lose some of the rational interpretation, but remain a model fitting method. And so you can do that. Now, sometimes things that we think are heuristics are actually consequences of a different mental model. And so an example in the foraging case that we realized was that if you make a decision based on the number of successive losses that you've had, that would be irrational according to the true world model, but it's rational according to a variant of that model, which has some kind of building up of probability in a certain way. And so the thing that my collaborators were referring to as a heuristic actually is optimal, but just in a way that they didn't know. Now that said, you don't necessarily need to know that in order to use the model to fit a heuristic, but it just gives you an extra richness of the interpretation. And it gives you new predictions for generalizing beyond things that you may have expected, because now you can say what the assumptions are and you can make predictions and manipulate those expectations.
Thank you.
Cool. Well, thanks everybody for listening and for your attention and your questions. I really appreciate it. And if you have further questions that you think of down the road, you can reach me via email, xaq@rice.edu. And I'm happy to entertain further questions if you have them. Looking forward to seeing Michael's talk. One apology, I'm not going to be here for the later sessions today because I am organizing my own workshop today, which is beginning in like 45 minutes. So thanks.
Okay, do we have more questions? Okay, so since we do not have more questions, thank you again for your really cool talk. And I'm really looking forward to the panel discussion that follows after Michael's talk.
Yeah, I do have time for the panel discussion. I was just looking at the time. It starts in 2 hours, not 1 hour.
Perfect.
Yeah. Sorry for any fear that evoked.
Yeah, you had me worried for a moment.
Okay, so we can go forward with the next talk. I think you should be able to share your screen now, Dr. Littman. So we don't hear you. Oh, yeah, perfect.
All right, that was my intro. Okay, all right, fine. That sounds good. Thanks for. Just wanted to double check a couple things to make sure I put it in my calendar correctly. So what's the time that I'm shooting for, and can you characterize the audience a little bit?
Yeah, of course. We are PhD students from the research training group called Computational Cognition at the University of Osnabrück. We have some more students, maybe masters or bachelor level students who are joining in the talk. You have 30 minutes for the talk and then followed by 15 minutes of discussion. And then we'll have the panel discussion with you and Xaq together.
Great.
Okay.
All right.
So I just wanted to introduce you very briefly. If sorry for the confusion. So yeah. So if for people who do not know, we have now with us Dr. Michael Littman. He's a professor and a computer scientist at the Department of Computer Science at Brown University. You've probably seen him at the Lex Friedman podcast, and he's one of the seminal authors of the reinforcement learning algorithms that started around the 90s. And I really want to welcome you to this group today. Thank you for being here.
Sure, it's all good. All right, yeah, thanks a lot for having me. It's nice to see some of you anyway, and see many names. And yeah, so I'm going to build a little bit on some of the models that Xaq was talking about. That was a great talk in terms of doing something that is actually computationally very tricky and using it as a window to see and understand complicated behavior in the world. So I'm going to focus in this talk on not real behavior in the world, but the behavior of reinforcement learning agents that are being asked to solve particular tasks, and maybe cast some doubt on how it is that they're doing what they're doing, and how we might move forward to understand and implement them better. So the focus is on assessing the robustness of deep reinforcement learning algorithms. So just to give you a little bit of the context of how I fell into this, we were interested in the problem of explainable reinforcement learning. So there was a number of really exciting results. For example, the DQN or Deep Q network that was shown to be able to play Atari video games at, by one argument, human-like level performance. And you watch these things play, and in some of the games, they're actually phenomenally good. And you think, okay, well, they've obviously learned something really, really great and powerful, but they're very opaque. They're very much a black box. And we'd like to be able to say, I understand what it is they're doing because we're going to do some analysis on the network and explain it. So we thought, okay, this is going to be important for using reinforcement learning in the real world, reinforcement learning agents that after they've run, you can look at them and say, okay, I understand what they're doing, and I believe that it's safe and reasonable to adopt that, right? So think about it in the context of something like a self-driving car, which you hope is going to actually turn back at the right time. And in a self-driving car, if you are sold the car and you're told, okay, well, we trained it in simulation and it seems to be great, so you should use it now to drive on the highway, that's really scary. So you want to have some reason to believe that the decisions that the algorithm are making are sensible. So that's what we've set out to do. And so we just trained an agent to play one particular video game akin to what folks at DeepMind had done. And then we tried to generate an explanation for it. And we failed terribly. And we started to wonder whether explanation was even possible for these kinds of networks. And the punchline of all this is that Q values, which Xaq mentioned in his talk, are kind of the seat of how the decision-making is made in these agents. And generalizing these Q values is really hard. And so I think in many cases, the agents are not doing it. And so it's very difficult to say in any generality what it is that they are doing. All right, so let me present this in terms of a case study. So this, if you grew up, if you're a kid in the 80s like me, like this is great. This is what video games are supposed to be. This is a screenshot from an Atari video game called Amidar, which you may have seen the video game Pac-Man. It's actually an awful lot like Pac-Man. There's a little yellow character. Yep.
Sorry to interrupt you, but I think your slides are not moving ahead, so we still see the first slide only.
Thanks. Yeah, it says sharing is paused. Bring your shared window to the front. I didn't notice that message. Pause. Bring your shared window to the front. Nope.
Now we see the Amidar.
Yeah, but it still gave me that warning message. This is I've been, I've obviously been like all of us in Zoom nonstop for the last 10 months. And I've never seen this particular message. Maybe it's because of the live aspect of it. I'm not sure. How do I, maybe I should stop sharing, then bring that window to the front, then start sharing, which of course I can't do because I have to bring.
Yeah, I couldn't do that either. I had to share first and then start the presentation.
Yeah, you have to, because you don't have the ability to share when you're at the presentation. All right, so here's a new theory. All right, I think I figured it out. So the problem was unimportant. The point is, I think it's fixed now. All right, so just to show you the boring slide that you missed is just text. So background. All right, now we've moved on to a picture. This is a screenshot, right? You knew it was not working because I said, this is a screenshot, and of course there was no screenshot. This is a screenshot of a video game called Amidar, which is an awful lot like Pac-Man. There's a little yellow player that actually looks a little bit like a Pac-Man pointing down on the screen, and it's navigating this kind of maze environment. It's being pursued by these little purple enemy agents, and it's trying to cover everything. It's trying to visit all the places on the screen. And as it fills in the track, you can see it changes color. Once it's filled in the entire track over the entire screen, the screen is completed, it gets a big bonus, and we move on to the next screen. All right, so this is one of the video games that was part of the test bed that was in the DeepMind work that kind of really initiated the whole study of deep reinforcement learning. All right, so we trained up an agent in this game, just our own agent, just like the DeepMind folks did. And here's some of the stuff that it does. So hopefully you can see this moving, maybe not super smoothly, but hopefully enough to notice that the yellow agent is moving around, deftly dodging these enemies, filling in parts of the screen. It's maybe not, you know, what Xaq would call optimal or even boundedly optimal, but it's doing some pretty amazing footwork to dodge around these agents. And then eventually it gets captured and ends the screen. So that was one run. Here's another. Again, you're seeing this pausing behavior so that it doesn't run into the enemies, and it's zigzagging through the maze and filling in pieces as it goes while avoiding the enemies. It looks great. Like I would have trouble moving that adeptly around on the screen so that I can fill in the different pieces. And you can see that it seems somewhat intentional about filling in the screen as it zigzags up and down. It doesn't look random. It's playing great. So you look at this and you say, yes, I want to understand how it's doing that. And so explain that. Okay. Oh, so why do we want to do this explanation? I kind of already talked about this. What we're expecting is that when we peered inside the agent, we would find that it knew to avoid enemies because we know that those are bad and it's clearly avoiding them. So we'd expect some kind of control algorithm inside of it that was actually identifying the enemies and then making a plan or something to avoid them. You'd think it would be seeking out unfilled lines on the screen so that it could fill them because that's how it completes the screen and succeeds. We know it didn't learn about corners. So there's an aspect of the game, like in Pac-Man, when you eat a big flashing pellet, a power pellet, you get powerful and then you can actually defeat the enemies for a little while. This game has that as well. We know that the agent didn't learn about that because we never saw it do it. It turns out if you get the boxes in all four corners, you get that powers you up for a little while and you can defeat the enemies. So we know it wasn't doing that, but we're expecting that it was avoiding enemies and seeking out unfilled lines to fill in. Maybe it had learned some evasive patterns. Maybe it learned priorities for filling in the board, like corners are secondary, center is important. That's the sort of stuff that we were hoping to find. And so to look for this, what we thought is that we treat it kind of like maybe a neuroscientist might or a cognitive scientist might by intervening and seeing how it behaved. So we could say, well, if it's the case that it's actually prioritizing this kind of block, then if we set up the world in a certain way, we should see it behaving in a corresponding way. Okay, that's what we were hoping. So we came up with a couple really simple little interventions that we could do because, you know, these video games are code and we can intervene in the code. The agents are code, we can intervene in the code. So we have, it's easy. We didn't have to put probes into anybody's brains or build anything in the physical world. We just had to tweak code. So here's the thing that we did. On the left, you can see the agent in the initial condition of the screen, except we filled in the first box. Right? The box where the agent is has already been filled in. So we gave it a little boost. It doesn't have to worry about that anymore, and it can proceed. So here's how the agent behaves given that. Okay, so it moved a little bit down, and then it sat around and died. All right, so that seemed not good. So we thought, okay, well, maybe it doesn't know what to do in this particular instance. Let's try something else. Let's get rid of all the enemies except for one. Right? This is a strictly easier problem now. There are fewer agents pursuing you. So this is what we see in that case. It did dodge around the agent, around the enemy, and then it kind of sat in the middle of the maze and twitched. A little more twitching, And eventually we realized that it was in an infinite twitch loop. So it's just going to sit there forever. As the enemy patrols the outside of the maze, the agent will sit there, I don't know, in mortal terror. It's really hard to tell exactly what's going on, but it's definitely not playing the game effectively. So this is that same agent control program that you saw a little while ago that was doing so well. It doesn't seem to really know anything about this game. It doesn't really know about avoiding enemies. It doesn't know about filling in the lines. It's totally confused. All right, I thought I may have heard a question, but maybe that wasn't a question. So
that was just me laughing at the mortal terror.
Okay. Thank you for that. Yeah. You know, when I give talks, I really like to kind of hear what people are thinking, and it's very hard in this new world. I'm sorry. I hope it doesn't mess things up too badly. All right, but anyway, so we can continue watching this forever, but it's really not that interesting after a while. So what's going on? We don't understand what why these agents that seem so great, we put them in a slightly easier environment, and then they seem to know zero, absolutely nothing. So one of the things that we did is we used a tool called the saliency plot, which is used to figure out, okay, what in the current input, what is it that the agent's actually paying attention to when it's deciding on its value predictions, like how good a situation am I in with respect to the future, and also what should I do next? What action should I take? And so the essence of this idea is that you can actually blur out chunks of the screen and then ask the agent, what would your choice be with the blurring or without the blurring? And if the blurring doesn't change anything, it's probably not that salient. But if blurring a particular area of the screen causes the agent to make very different predictions about the action it wants to take or its prediction of future value, that's probably an important part of the screen. And we light that up in red or blue in this case. All right. And so if you look at some of these little...
I have a question, Michael.
Yeah.
If you blur it, now it's very much outside of the training data. So, maybe all of the features that it had learned were dedicated to fine structures, and then there are none of those. So it would pay attention, but it just can't see it now with the blur.
Well, the test is, make sure I understand the question right. So the test is we blur an area and then we ask, we stop the agent, we freeze it in the middle of the thing. We don't run the whole game this way. We just say, at this particular moment, if I blur this part of the screen, what action would you choose? And is it the same as the action you would have chosen if the blurring wasn't there? If we can modify the screen and it doesn't change anything, then by some definition, it's not paying attention to that part of the screen, right? But if we change a part of the screen and it does change the action, then it has to be paying attention to that part of the screen, right? So there's an assumption here that it's not the case that the agent is taking the entire array of pixels and using every single one of them in some complicated function to decide what to do next, that some pieces of the screen are more important or more salient than others with respect to a particular decision.
Yeah, I guess you could have something which is compensating, but that's very unlikely. Okay, so thanks.
Yeah, and we run it and we look to see what, you're right. It could be compensating, or it could be paying attention to everything, and it's just hard to tell. But we do see some really interesting patterns of what tends to light up in this case. So if you look at some of these screenshots, it almost always is paying attention to itself, which seems very sensible. Like, it needs to know where it is on the screen, and if you were to take that away and it couldn't see that part of the screen anymore, it wouldn't know what to do. But you can also see in a bunch of these frames that it's paying attention to the score. So like the far left corner, the 0 is a little bit lit up, and the 1, 2, 3, 4, the fifth screen over, the 6 is lit up kind of brightly. See, some of the pieces of the maze are lit up well, and that seems okay. But the fact that the score is lit up surprised us. You wouldn't think that that would be the most important thing to pay attention to when you're deciding what action to take, because there's very little information in the score, you'd think. More information about the past than the present. Oh, actually, okay, I have an animation of this. So you can actually see it's pretty consistent from moment to moment. There's little bright lops that happen, but if there's a spotlight on the score, it tends to be there for a while. If the spotlight on the agent tends to be there for a while. And so, yeah, it's not definitive, but it's giving some evidence that it's paying attention to parts of the screen that we were surprised that it was paying attention to. The player and the score. What we eventually realized, before I show this video, what we eventually realized is that the reason for this is we run the agent, we train the agent in the same environment over and over and over again, and it starts to learn a lot about the states that it is in when we run it, right? So it basically, I like to think of it as it kind of carves a groove in the state space. That it's the part of the state space that it visits in the same order, in the same way, over and over again. This particular game, and it turns out almost all the Atari games, are at core deterministic. So if we put the agent in the same initial conditions and we run it again with the same deterministic policy, it's going to visit exactly the same sequence of states. Is that good? I don't think so. Is it realistic? Not really, but it is actually a property of this game, and it is a property of these learning algorithms that they will start to learn a lot about the states that are visited on that path, potentially to the detriment of any other states in the environment. And so one of the reasons that the score ends up being a really important feature is because the score is advancing nicely as the agent is moving through the world. It kind of is, it's like it's reading a pre-printed book, and that's kind of the finger that's keeping track of where it is in the book. It has memorized a kind of choreography, a dance, and it's just executing that same choreography over and over again. It's learning correct values for the states along that path with respect to its behavior, but it's not learning about the whole state space. It's not learning about the problem. It's learning a particular sequence of moves that actually seem to be effective. And this is a thing that people in my group have actually looked at in the past in other video games. This is a Mario world kind of thing that you can see the agent, again, behaving really deftly, moving through the enemies, around the enemies, bouncing off of the enemies, jumping over the gaps and so forth. And unlike in Xaq's talk, where the agent is actually making an observation and conditioning its behavior on that, this agent is entirely blind. The only reason that it's working at all is because it found a particular sequence of moves that if you play them back exactly will cause good behavior in the game. So it's not really taking into consideration the situation at all. It's exploiting the fact that the environment is deterministic. So the thing that's going to work, the thing that's worked in the past is going to work again.
Is this environment something which is repeating?
No, but it is deterministic. So it got through that whole level, and if we reset it to the beginning and it does exactly those same joystick twitches, it would do exactly the same thing. I
see. Okay.
This particular work, what we were really getting at is the point that policy space is often much richer in terms of reward than you give it credit for. Like we try to make these agents that they're making sophisticated decisions. It turns out that if it just tried a couple of things, it's going to hit on something good. But that wasn't the point here. The point here is just that it's really easy for us as observers to mistake memorized patterns for intelligent decisions. And this is reminiscent of issues that happen in the supervised learning setting as well. So in supervised learning, there's training examples, and you could talk about, well, what are the different ways that we might actually make an output based on an input? So if a particular input was one of the training examples, we can just memorize it and report it back. But in many cases, we have to do some kind of interpolation. We say, well, the pattern of results, the pattern of input-output pairs that we've seen is like this, and so we can actually make guesses at states or inputs that we haven't seen. But really, they need to be examples from the same distribution. If we vary the distribution of inputs dramatically, then we're really in the extrapolation phase where we're making predictions far out of the sample, and that's a much harder thing to do. You wouldn't expect that to work particularly well. And so these are kind of weakest to strongest in terms of measures of generalization. Like doing well on the training examples isn't really saying anything in terms of generalization. Interpolation is kind of a weak generalization, and extrapolation is a very strong kind of generalization. And when we're doing reinforcement learning, we have analogs of these exact three levels, right? So the training examples you can think of as being the on-policy states, basically the things that we visit, the agent visits over and over again during training because it's part of the way that it's actually behaving. Interpolation could be, well, off-policy states, states that maybe we encountered during training, but we don't tend to encounter them when we're behaving in the environment because our policy doesn't direct us there, but they're maybe close enough that we can make guesses about what happens at those states. And then extrapolation would be, well, what about a state that we can't reach? It's actually impossible to reach, but it behaves perhaps similarly to the states that we did visit. Like we'd like to be able to say something about those other states that we've never seen, we can't see, but if we were somehow magically placed there, we should be able to do something sensible if we have a policy that really is generalizing. And well, the punchline here is that the way that we typically train these reinforcement learning agents gives it a tremendous amount of information about those on-policy states, those situations in the environment that come up when we actually run the policy. A little bit of experience on the off-policy states, and basically none at all on the unreachable states. And your typical reinforcement learning algorithm, your typical deep reinforcement learning algorithm, is going to ignore those states entirely. There's nothing encouraging the agent to adopt a representation that generalizes to those states that it doesn't see. All right, so we wanted to kind of test out this idea. Let's see how we're doing here. All right, so if it's a half-hour talk, then I've got 7 minutes left. So let me kind of skip ahead a little bit. Basically, the upshot here is that we found that the agents, for the on-policy states, they actually do a really good job of predicting what the future is going to look like, how much value it's going to obtain if it continues to behave this way. And so the value error is low, and its prediction of the total accumulated reward is very accurate. And what we find is that when its predictions tend to break down, like if it reaches a situation where it's not accurate anymore, everything falls apart simultaneously because it really doesn't have a very deep or nuanced understanding of the environment that it's in. The agent has basically memorized a behavior pattern, and as soon as we get off that behavior pattern or off of the set of states where that behavior pattern applies, everything just collapses. It's a very non-robust kind of agent. If we present it with novel states that it's never seen before by manipulating the environment in various ways, it knows that it doesn't know them. It knows that they're sort of unrecognized, but it just produces garbage as output. It doesn't know what action to choose, and it doesn't know what future value to predict. So we wanted to improve generalization. And so in supervised learning, if you improve generalization, one way to do that is, well, give it a lot more data. That tends to help an awful lot. And another one is to do some kind of model regularization. So you don't let it memorize everything, force it to represent everything more compactly, and that forces it to generalize not just within the states that it's seeing, but also to states that it's not seeing. It tries to find a more self-consistent, simpler predictive rule. And so we can do this sort of thing in reinforcement learning as well. We can let it run longer. We can diversify the training by starting it in random starting positions instead of always the same starting position, forcing it to explore, see more of the state space. And we can reduce the model capacity. We can change the network so that it just can't memorize so many things because there's just not enough neurons there. And what we find is that these things help, not as much as we hoped, but to some degree. So I do see that there are some messages in the chat, but I have no good way of seeing the chat while giving the talk. So if anybody sees that or wants to call out anything, let me know. Or I could also get to it.
It was about when we couldn't see your slides, but there's nothing new since then. So it's all good. Thanks.
All right, thank you. Thanks for clarifying. All right, so I wanted to do a quick other kind of case study that we looked at where we're starting to see something a little bit more promising. Like that first study, I was very depressed afterwards because it's like these learning algorithms seem to be doing so great, but the thing that they're doing, it's what we told them to do, but it's not what we wanted them to do. And so maybe there are better ways of telling them what to do. And so we adopted a methodology from Cobb et al. 2019, which is very much like what you do in supervised learning. So instead of just saying, hey, we're going to run and revisit our training data over and over and over again and memorize our training data, which the supervised learning people discovered in the 90s was a really bad idea, maybe even the late 80s. Reinforcement learners are still kind of in this same place, and we need to get out of it. And so we looked at an environment called CoinRun, which what the nice thing about CoinRun is instead of it being one environment and you run it over and over again, it generates many, many, many random levels that have the same underlying physics. It's the same game, but the background is different. The location of the obstacles is different. If an agent can do well on a new one of these randomly generated levels, it must be because it's really starting to understand the space of possibilities. So what we found is that not so surprising, well, what they found and then we replicated was not so surprisingly, if you give the agent lots of training levels, lots of screens of this game, you know, tens of thousands of them, and train it up on that, then on any of the particular levels, it's actually going to be doing worse. But on newly generated levels, on a test set of levels, it's actually going to be doing better. The more training levels that we show it, the better it's going to be doing on the test set, and the worse it's going to be doing on the training set until those things come into alignment with one another. And that's when we're actually doing a proper generalization. And so we see that in supervised learning, we see that in reinforcement learning, but only when we do this trick of having a sort of inexhaustible supply of test environments that it can train on, right? Where the differences between them reflect the differences that we expect to see in novel situations at testing time. We did find that some algorithms and some network structures are more effective at this kind of generalization than others. And it's something that's not so obvious from just looking at their performance when learning on a single level, but you start to see differences in terms of how effectively they actually generalize across different scenarios. We've been finding that policy search is really effective at this, which makes me very sad because, you know, as Xaq mentioned in his talk, model-based methods have tremendous advantages, but model-based methods have not yet been effective in deep reinforcement learning. Almost all the experiments that have used a model-based method, well, all the ones that claim to use a model-based method either haven't worked or they're not actually a model-based method. And so it's been a kind of a negative result so far. The thing that we think is really necessary for agents that are actually reasoning about their environments is something that we have not gotten to work in the new, you know, deep learning era. All right, so just to summarize the little quick tour that we got here. In the deep reinforcement learning world, when you see good reinforcement learning performance, you should look a little closer at it. There are ways that these agents can look like they're doing well, but they're not actually learning what it looks like they're learning. So it's important to keep that in mind. There is an analogy to be made between reinforcement learning and supervised learning. It's subtle and it's a little difficult to apply. I said this in front of Rich Sutton, who you know, arguably one of the fathers of reinforcement learning. And he got very mad at me because he's like, I don't want to separate things into training set and test sets. To me, reinforcement learning is about acting in the world, and the world doesn't really separate itself into training sets and test sets. I'm like, you're right, Rich. Of course you're right, but you're wrong. Because like, if we don't do this, at least in the development of algorithms, we're going to generate algorithms that look like they're doing something reasonable that are actually not. And so this is a really important mechanism for keeping us honest during the development phase. Ideally, eventually, we want agents that can live long, you know, productive, healthy lives, and they don't have this notion of we're training and later we're testing. But I think to get that, there's a tremendous benefit for looking at the world the way that the supervised learning people have done. All right, and yeah, so I still want the last line there. I still want model-based reinforcement learning to work. So I've got some students working on learning abstracted models, learning about the objects in the environment and how they interact, the sorts of things that we do when we play a video game like this, or like live in a world like we do, where we parse things up into things and properties of those things. These networks are not being encouraged to do that. And so we want to generate networks that really have that as a bias, that they're trying to break the world into objects, think about the interactions of those objects. Maybe those kinds of models will generalize in a way that we haven't yet seen with current model-based approaches and even with policy search and Q function-based approaches. All right, cool. That was my thought. Thanks.
Thank you. This was quite nice. We're open for questions now, so please raise your Zoom hand if you have questions.
Zoom hand. I want to call on Michael just because he's like in the question part of my screen at the moment. But yeah, oh, he disappeared. Oh, Vivian has a question. And then Michael has a question. All right, well, Vivian.
I was actually wondering, so in the end, you showed some results from using proximal policy optimization. And I was just wondering if you think that policy gradient methods have some advantage in this case over value methods like DQN, because I guess obviously the score or the time left is very useful to make a value estimate. And maybe sometimes it's more straightforward to learn a policy actually instead of value estimates. So do you think that has an effect on this?
I think that's absolutely what's going on here, is that for what these networks can do most easily, predicting the next action to take given the way that the screen is arranged versus predicting the long-term future value of what's going to happen next, the actions are generalizing better in these games, right? And so doing a policy search, a direct policy search, does seem to produce more generalizable results. I don't think that's a necessary property of these games, but it is something about the environment and what the algorithms themselves find easy to do. And like I said in the very beginning of the talk, I think generalizing Q values to unseen states, like I've never been in this situation before, I'm now going to just use a neural network to predict basically how long am I going to last? Like how well am I going to play from here? That's really difficult to do. I think even people, if you ask people to do it, what they're going to do is a kind of mental simulation. They're going to do something more like a model-based search and try to project forward. If you don't have the model and you're asked to make this prediction without the ability to kind of iterate, it's just really hard. And so the best it can do is memorize the states that it's seen. It can't really handle novel states. Policy search, policy gradient methods that are just representing the policy. Well, if you've learned a policy, like don't run into the bad agent, that still works, right? You move that into a new state that you've never seen before, it's still a sensible thing to do. So I think that's what we're seeing.
Yeah, it's actually impressive under that light that they can even learn to perform the game.
I know, right? Man, these networks are weirdly successful.
Yeah. Right, yeah, thanks.
Oh, yeah, sorry, Vivian. Okay, all right, Michael.
So I've kind of straightforward question I had, and I have one kind of random one that I don't know how relevant or useful it is, but I noticed when you were talking about the determinism of these video games, and actually I was never really into video games, and recently with Corona I've been playing more, and I've noticed that it seems like they could have been designed to be much more random and stochastic than they actually are, and kind of the way enemies and things show up is very much deterministic, which interestingly seems it's a property of the training data that you're using when you're using these deterministic systems. So aren't there more stochastic video games, and are there experiments you can do where you can see if generalization is better with such data?
Yeah. So I would say two things. One is that I think the effect that we're seeing is not strictly due to determinism, but it's so much easier to see in the deterministic setting because the patterns just are so consistent. If it was a noisy environment, we'd still see it mainly learning about the states that it mainly visits. And so there'd be a decrease in performance, but it wouldn't be as dramatic as what we're seeing. And so I think it's just harder to see what's going on. That said, it does better, right? Because if it's a stochastic environment, the agent is going to see more of the environment. And at some point, it's going to start to push up against its ability to memorize. And that is going to put pressure on it to generalize better. So we do see improvements when we diversify the set of states visited, either because the environment is stochastic or because we actually just push it. Like we intervene on the agent while it's learning and like force it to take random actions that kind of stochastify the environment. The one other thing I want to mention, though, and then I'll pick up Xaq, is that we were really curious about this too, because a lot of the emphasis in the reinforcement learning community since the OG days is that the planning community in AI focused on deterministic environments, but we reinforcement learning people, we focused on stochastic environments. And we were surprised that these environments were so not stochastic. Part of it is they don't have to design the games this way because people are a little bit unpredictable. It's very difficult for a person to execute exactly the same sequence of actions every time they play. In fact, people who play Pac-Man in the arcade, the people who are awesome at this learned how to be very predictable and execute the same pattern over and over again. It's very difficult for people to do that. And so the game designers didn't really worry about it. But we did an analysis of all the games in the DeepMind testbed and tested to see whether they were stochastic at all. And even the ones that look a little bit stochastic are actually not. It was something like 2 of the games actually had any kind of non-determinism in them at all. And that was really surprising to us. It turns out that you can express non-determinism in the Atari game by the console. When it's initialized, the untouched memory is actually random, and some games keep that untouched part of the memory clear and read from it to use it as a kind of random number seed. But really just 2 games out of the ton that we looked at. And even then, the randomness wasn't particularly interesting or consistent. So yeah, I don't know. That was too many answers to one question. Sorry. Xaq was waving his hand at one point. Yeah.
Sure. Thank you. Very, very cool talk. One of the, so we've been thinking a lot about robustness in terms of object recognition and other things like this. And the generalization is, of course, the key question outside of the training data. So a lot of that comes down to good representation learning. And so I'm wondering to what degree you think that good representation learning would be helpful here or not. I suspect that it would not be, but perhaps joint representation learning and reinforcement learning would be useful, because representation learning, you're trying to compress what you see. And in these video games, that might mean that you just, let's say in the ideal case, you find a graph, but that doesn't mean that you're going to explore the graph well. You might be still doing a stupid thing on the graph, even if it's really compressed. Whereas if you do representations that are predictive of your future value, that might help in a different way.
I see. Well, what we're trying to focus on is are representations that allow us to predict future states, so we can build models. But you're right. So if it could learn a representation that helped predict future value, that should help. But I think what you led with, the idea that you really need representation learning and the action learning, like learning how to actually behave in that environment, you need them to be working together, because the representation you need is one that supports the actions that you're taking. And the actions you're taking, well, they're going to be terrible unless there's a representation undergirding it to allow it to make accurate predictions about the future. So I think that's one of the reasons that we're not seeing this happen very well.
I wonder what would happen if you actually tried to, instead of giving it the full video game, if you gave it just the graph, which, I mean, then the representation is much more compact, but I suspect you would still have the problem of, I mean, it would be faster, so you could do more training and such, but you might not explore the kind of policies that you'd hope for in that case, even though you have a great representation.
You're saying the input representation of the current state, we could basically pre-abstract it into, well, there's just a couple places you can be. There's a couple things that indicate whether or not that place has been visited before, yes or no. We'll just present that. Yeah, you're right. I mean, I think the way to get at this, though, is similar. It's an analogy to how the deep learning people have dealt with vision, right? Visual recognition. And that is that you create a bias in the network structure that encourages it to learn a certain kind of representation. So in their setting, they use convolutional units, right? Why convolutional units? Shouldn't be necessary. In fact, if you put in convolutional units, you're actually limiting the expressivity of the network. So like, how could that be a good thing? And the answer is, well, it kind of forces the agent to learn to recognize patches, right? And to recognize the patch in the same way, no matter where it exists on the screen. And so information about a particular patch in a particular part of the screen is sort of forcibly generalized to the rest of the image input. And
so you're suggesting like a convolutional policy?
Well, so I think it's objects that we need to encourage the network to break the world up into objects, because first of all, that's how these games are programmed. Second of all, it's sort of how intuitively we think of the world. And third of all, it's going to give it the right primitives so that it can reassemble them into predictions about the future. Right.
Like, what I was suggesting is that even if you did that with like a perfect graph representation with, localized agents, that it would still do bad policies, because you have to do something to get it off policy or explore or generalize across different parts. Even if you know that this is an object, it doesn't mean you handle it well.
Sure. Okay. All right. So maybe you're arguing that an object representation is not sufficient but maybe is necessary, but you didn't argue for necessary, but you argued for not sufficient. I agree with not sufficient. Like, I think that a good object representation supports exploration, smart exploration. In fact, all right, not to make this about me, I'm gonna make this a little bit about me, I'm sorry. So we were the first ones to look at these Atari video games as a test bed for reinforcement learning. We looked at a particular game called Pitfall, and we didn't know this was pre-convolutional nets, or at least pre-deep learning convolutional nets. So we just hand built an extractor for the objects on the screen, and we forced the agent to learn, okay, well, there's objects. The thing you're trying to learn is what happens when these objects interact in various ways, if they say touch or one's on top of the other. There's various properties that these objects can have in the screen. That's all you're trying to learn about. And you're going to generate exploration actions to discover what happens when objects come together that hadn't come together before. We ran it in Pitfall, and what it did is it systematically explored. It's like it went over and touched a hole and realized it would fall through the hole, so then it didn't do that anymore. And then it found a ladder and it discovered how it could move up and down on the ladder. And then it just mastered the screen. We put it back in that environment and it just, boom, right to the end. We put it in, we didn't do this test, but the information that it had, if we gave it a slightly different screen with the pit in a slightly different place, it would have planned perfectly, right? It knew what it needed to know to work in that screen. The making it about me part is, folks at Alberta picked up on that work. They created an entire test bed. The DeepMind people applied deep reinforcement learning to that test bed, and then they got bought for $500 million or whatever. So it's all fine. I'm not bitter. I'm not saying I'm bitter. Who said that I was bitter? But the point is that that it was what kind of started this whole train going was the idea. Wait a second. We should be doing reinforcement learning around objects. And then it got lost along the way, and it would be good in the deep learning era to kind of bring it back in, because yeah, our performance in Pitfall is so much better than even the best deep learners at the moment. Cool. So that may bring us to the Ashima.
So if you do deep learning on objects, do you then learn the actions available for particular objects then, or do you learn some other mechanism of being in the environment?
Right. So there's so many things you can do once you have that representation at your disposal. So what we were imagining doing first was something like planning, right? Basically, you've built a model that says, I look at the screen, I look at the pixels on the screen, but I actually break it up into a small number of objects. There's like 20 objects, and here's where they are. Here's their current status. Then I have a deep network that's able to predict what happens when objects of certain types interact, right? What tends to be the thing that happens next? How does it change the attributes of those objects, right? So it's like an object representation to object representation model. Then what we do is we say, okay, now let's just look ahead. I have to make an action choice right now. Let me just think of it as a planning problem. I'm going to imagine for all the actions I could take, how that would change the world. For the actions I could take from there, how that would change the world. This is computationally very expensive, but it should allow us to at least look somewhat deeply into the future to decide what the right thing to do is now. If that works, then we're going to be stuck with the problem of it's not efficient. We need to make it more efficient. And that can bring in all sorts of ideas that are being used elsewhere, like networks that are proposing reasonable actions, right? So not just here's the action I should take right now, but like here's 6 actions that might be worth a little bit more, more attention. So this is how the DeepMind people have done so well in games like Go. That Go has this incredibly deep and incredibly bushy tree that you can't search. You can't search exhaustively. But networks learn, hey, when I'm in this kind of situation, these kinds of stone placements tend to be good. And now I can use that information to do a deeper search from those states. And there's reason to believe that psychologically people work this way as well. We don't consider every possible muscle twitch at every moment. We have some ability to generate what are sensible things to consider. And then we can do deeper, I don't know, it's like system 2 kind of processing on those states to evaluate whether they actually are worth doing. But we can't consider everything. And these networks ultimately can't consider everything either.
Mm-hmm. Thank you. Georg?
Yeah, thanks for the very interesting talk. I'm actually wanted to ask about AlphaGo, AlphaZero, and the like, but you just mentioned it now, so I took took the courage to actually ask the question.
Great.
How much did you look into robustness of these algorithms?
Yeah. So I mean, we don't have probable access to AlphaGo, so we did not do any kind of probing of that. But at least AlphaGo, there is reason to believe that it actually is handling things fairly generally, that it's actually learning a reasonable representation of the game and what happens in that game, as evidenced by the fact that people have started to really dig in and say, okay, well, what does it do in this situation and why? What does it do in this situation and why? In many cases, it agrees exactly with what an expert would say, but then when it disagrees, it says you should place the stone here, expert says you should place the stone there. Who's right? They can kind of play the game forward a little bit and see, well, what are the implications of that? And pretty consistently, AlphaGo is right. Like its decision about what to do in cases when it disagrees with people tends to be correct, as best we can tell, right? It's still an astronomically big state space and we don't really know, but the digging in that people have done indicate that it does seem to be generalizing well. So that's okay, so you could take that as evidence that the thesis of my talk is incorrect, that I said these deep reinforcement learning systems aren't generalizing. I think most of them aren't generalizing. I think that one maybe is generalizing, or maybe we just don't know. But it does seem to be doing a really good job.
Actually, yeah, but I think I'm a bit more involved with different open source projects which reproduce it, and it, well, most of the cases experts agree, but there are actually quite a few situations. None of the at least openly available bots get right, while experts obviously agree. And if you show the specific line to the AI, it tends to agree after a few moves, but completely misses it. Same as happened in the famous game 4 of AlphaGo against Lee Sedol, where it agreed after a few moves, but it was too late by then. And there are even there's one project, Minigo. Don't know if you've heard of the name. They basically just set out to reproduce the AlphaGo thing, and they had 3 consecutive runs where it confidently said, yeah, this is the best first move, but it was 3 different moves. And well, I'm actually doing my project on kind of the dynamics of this, and it's, well, it definitely isn't. There's some, even through the environment is deterministic. The training dynamics are far from deterministic, and there are quite a few, well, pitfalls in it. And thanks for appreciating that one. So it's far from trivial, and the at least the original formula DeepMind used introduces some kind of well, non-determinism in the whole process, and also non-reproducibility, which makes, well, the claims in the paper, at least to some extent, well, you should question them for sure.
Okay.
But thanks for the answer.
No, thank you for the background. That is really, really interesting. So it kind of, I mean, I think what you're seeing is kind of agreeing with what I'm seeing, which is that even in cases where it looks like it's got insight, it doesn't necessarily have insight. There isn't necessarily anything behind it. It's just that it happens to handle that situation well, but in similar situations, it might break down.
Yeah, we definitely see that in this interpolation with this extrapolation stuff, that it can't extrapolate. It can interpolate pretty well. It can learn statistics of the game perfectly well, but everything I have seen so far is pretty sure that it can't extrapolate.
Yeah, that seems to be a pattern we're seeing with deep nets, is that they are almost magically good at interpolating, but they typically do not extrapolate. Cool, thank you for sharing that. All right, are we in panel mode now? What's the situation?
We are in panel mode. The plan was that we ask questions to both of you. So, once Xaq answers, once you answer, and then hopefully we have a much more informal discussion. Xaq, please.
I have a question for the other panelists.
I was going to do the same thing, but you beat me to it.
So when you include a variety of different versions of the task, lots of different configurations, the hope is that it will learn better because it can't rely on some of these predefined features. I wonder to what degree it would be helpful to generalize even entirely across tasks, like different games, based on some of the same representations. Like we have a notion of an object, which in one case might be a little yellow sprite moving around. In another case, it might look totally different, but it still is like a coherent thing moving around. I imagine it's also hard to get that level of abstraction. But if you did something like, I don't know, compressed unsupervised learning or self-supervised learning or predictive learning that finds a representation across tasks and even a policy that would work across tasks, that like there are typical kinds of things you do, like there's stuff you avoid and stuff you approach, that maybe that would generalize better. Have people tried that?
No, not that. I mean, I think there's an analogy that people are considering, which is similar to what you're bringing out, which is that certainly in the textual domain with deep learning, the idea of learning from billions and billions of words of text in an unsupervised manner, it does seem to be forcing networks to learn something about the deep structure of language. And then the thing that's learned at the end of that can be repurposed in lots of different ways without having to retrain it, or maybe a little mild retraining in some of the bottom layers. But my understanding is that was starting to happen in the visual domain as well, where people are making predictions in images by sort of hiding a chunk of the image and having things being predicted from that. And that also seems to be generating really kind of a deeper understanding about how images are generated. Why can't we do that in the action domain as well? And so I have that same feeling. I haven't seen anyone do it successfully. I think one of the challenges to doing it is that, what are the language and the vision people have that we don't have? Lots and lots of static data, the very notion of a data set, right? Whereas in action domains, reinforcement learning domains, you really need to be able to act, right? Part of what we want it to generalize is, when I see it this way and do this kind of thing, this is what tends to respond, right? So the agent's role in the data ends up being really important in a way that I don't think we can just translate what they're doing in GPT-3 into the RL setting and expect anything interesting to happen. So there's kind of a conceptual hole still.
This may depend on the distance, the forecasting that you have to do. Like if you can do a short look ahead, maybe you can treat those as little simple movies and at least get a leg up on climbing the more difficult ladder. But I don't know to what extent the short-term thinking versus long-term thinking is useful. It seems like a lot of animals who are pretty successful in the world do a lot of short-term thinking. So it might be more successful than we would expect.
Yeah, and if you look at the language produced by some of these unsupervised models, they're not great at long-term thinking, but they're really good at the short-term thinking, and to the extent that it is really difficult to tell that it's not the sort of thing a person would say. You have to look closely. I don't know. Yeah, I mean, I think we could make something that looked at first blush to be a reasonable reinforcement learning agent this way, but then it's going to make all kinds of really stupid mistakes. And I feel like in reinforcement learning, it bites you sooner when you make stupid mistakes because the world starts to spiral out of control. Whereas, here's a story, a news story written by one of these things, and it kind of drifts off and suddenly it's about unicorns, but you didn't really notice because it was gradual. It's harder to do that in RL.
The feedback loop is really important. And that's something that, right, absolutely. You get, and the spiraling out of control is a hallmark of that feedback loop. Like if you're doing this and then you start to careen more and more wildly, then that becomes a problem. But if you only are restricted to it, I imagine it's like dancing, right? When you learn dancing, you have a dance teacher who keeps you in the right domain, right? They like hold you in the right place for a while, and then gradually lets you go. Or riding a bike, right? When you're being taught to ride a bike, you don't just start, or walking, right? You have something which gets you in the right zone first, and then gradually you can generalize beyond that. So maybe the right kind of curriculum learning or the curriculum teaching is something that would be really important for long-term thinking, but you could do some good short-term thinking on your own.
One of the things that we tend to see is that if you try to train an agent to behave using learning from demonstration, so you basically show it, you drive the car through a course and then you let the agent do it after that. And it just learns, okay, well, in this situation, the person did this, so I'm going to try to do that. It almost always fails because of the spiraling out of control thing, where it makes a small mistake at some point and that puts it into a part of the state space that it's never seen before, where it doesn't know what to do. So it does something crazy and it just, everything's off the rails. All the fixes that I've seen for that involve closing that feedback loop with an expert, right? So either the agent itself has to have a closed feedback loop and it's learning from its own failure, or you have a protective, envelope agent, like what you were suggesting, Xaq. But that agent needs to be pretty cognizant of what's going on too, and needs to be part of that feedback loop and controlling and shifting and pushing intelligently. Dagger, I think, is one of the approaches that's been wildly successful here, and it has that property that there has to be a smart teacher. It's not enough to just like, here's a bunch of recorded data, make sense of this. There's always somebody, in the moment.
Right, and if we're trying to learn it for the first time, we don't have a teacher like that. Like there may be a new task that nobody's ever solved before, so that wouldn't work.
Yeah, though, I've been feeling lately like we put too much emphasis on that in AI, that like humans are pretty smart, but we wouldn't be nearly so smart if we were doing that all the time. Like we learn from each other and we learn from worlds and we learn to solve problems that other people have already solved. And all the hints are then put there for us. And there's some of us, let's say researchers, because I think we're great. Like people like you guys who are really trying to do something new and different, but that's not most of what people are doing most of the time. I think that mostly what we're doing is we are in situations that we've been trained to handle because from birth, we've been given the right kinds of experience. And I don't know. I mean, not that I don't want to solve those other things. I love those other things. But I think that basically saying, well, we're not really doing reinforcement learning unless we're doing that. Yeah, that's a high bar. It's an unnecessarily high bar. There's tons to learn about just learning from each other.
Looks like Philip's had his hand up for a while. Maybe Philip, you want to share your question?
Oh, and unmute.
We can do some lip reading, but I'm not very good at that.
You do mind reading though, right? That's what I was hoping to learn from your talk.
I just wanted to try. So
with math.
It's a rather general question and more regarding the first talk, I think.
Philip, your volume is very low.
One second.
You said a question mostly regarding your talk.
How's it now?
That's good.
Okay, so it's a rather general question, but in the first talk you introduced several uncertainties about the world and the transitions, for example. And so, but in the real world, there's also a lot of uncertainty about the reward. Often it's not even uncertain what the reward even is. For example, in problems like, more basic stuff, like, for example, eye movements or motor control, I mean, it's not really clear what the exact reward of an action is, right? So, perhaps you can elaborate your thought on that, because, I'm a bit stuck there.
Sure, yeah. So if you're going to use reinforcement learning at all, you need to have something that you're trying to optimize. And so usually you refer to that as a utility. And you can put in anything you want into the utility function that you then optimize. Sometimes people actually put in an explicit term for like curiosity or a benefit from like info taxes is an example, where you put into the loss function explicitly a reduction in uncertainty about the state of the world. But you need something that you're trying to do. You can imagine that you could also learn without any reinforcement learning. You could learn a mental model and you wouldn't be directed in any particular way, but you still have a loss function that you're trying to optimize. Like you're trying to predict the future. That would be one example of a loss function that's not a reinforcing signal. And so I think for humans especially, and maybe for agents more generally, we have an intrinsic drive to gain information and to learn and understand things. And that's why kids play. And that's why it's good to encourage kids to play. It's one of the major routes by which we understand the world. And so it's not that and I would say that I would count that as intrinsic motivation. And that's a subjective utility that we would have to infer. We can't tell someone what it is. We can only infer it from that. And maybe there are some consistent brain mechanisms that reward the collection of information. Like, I don't know, there's some dopamine that would be released. Like, dopamine is kind of your intrinsic reward. It's not tied to anything particular in the world. It's like what your neurons are trying to optimize in a mechanistic sense. And we then relate that and interpret that in the context of things happening in the world. Like, oh, you got a cookie. Well, why is that rewarding to get a cookie? Now you're just like chewing something, you hear something, you taste something. So what? Like, why is that a good thing? It's a good thing because it's a good thing. It's intrinsically valuable. And so we would like to know, what is it that's intrinsically valuable? And some of it is sensory data. Some of it may be more abstract, like reduction of uncertainty. It's a great question. Michael, if you or if anybody else has any other thoughts on that, I'm just kind of inventing this as we go, but I think it's an important question.
Yeah, to me, it also relates to a question, I forget who asked it, but earlier there was a question about the rational behavior and whether economics is sort of drifting towards, okay, well, maybe behavior, the actions are not always really rational. The answer that Xaq was giving was in terms of, well, it can be boundedly rational, right? It could be the case that it's still trying to maximize reward, but there's limitations to how possible that is in some cases. But it could also be that reward isn't the right measure of what an agent wants. And it seems to me that this question also kind of gets at that lower level concern, which is, well, maybe rewards is just a made up thing that is obviously helpful for explaining a lot, but maybe there's limitations to it as well. And so I've been thinking about that a lot lately, but not usefully. I mean, for me, what focused my attention on this idea was that there was a movement in 2015 that still exists now, but it was really very intense then. And I don't know if everybody saw this, but I saw it a lot. And that was that there was a group of people who were concerned that we were going to build AI systems building on top of this sort of deep learning idea that would become very, very powerful and subvert humanity and ultimately kill us all. And it sounds like science fiction because, well, that is a thing from science fiction. But some people were legitimately riled up about this particular issue, and it often would come down to one particular thing, which is we think that reinforcement learning, basically deep reinforcement learning, is going to be the way that we create something that's generally artificially intelligent, right? The dream of the mega brain. It was going to be super intelligent because it wouldn't have all our limitations and biases. It would be this huge, powerful computer. And it would be trying to maximize reward. And the danger was we get to define the reward function when we build the system. It doesn't pick its own reward function. But whatever it is that we pick, it will optimize with laser focus, right? And there is no reward function that we could think of that would cause an intelligent agent not to ultimately kill us all. And so I was like, okay, I have a lot of issues with this, but one of them is, well, who says it has to be reward functions? Who are these stupid, reinforcement learning people who are telling everybody that it's all about reward functions? Oh, wait, that was me. So I started to wonder, well, is that right? Like, why don't humans have this issue? Why don't we pursue our reward with such laser focus that we destroy the world? And there's lots of directions to take that thought, right? One is, well, we're not smart enough. The other one is, actually we are, and we're doing it, and look what we're doing to the environment and the world, and we are going to actually destroy ourselves. And then another one is like, well, yes, but we don't have a reward function that all our behavior is focused on creating. We have a more complicated system and rewards that sort of come and go and that shift over time, and that we haven't characterized it perfectly in any mathematical formalism at this point. And that you can't maybe have intelligent behavior based on the reinforcement learning model we have now. Like the best that that can do is something that very quickly, puts itself into a loop and offs itself. And it will never become strong enough to take over the world because you can't handle the truth. You can't handle the complexity of the environment with such a narrow kind of agent. You need to be more like us. We're just kind of motivated by lots of things. So I don't know. I don't know exactly where to take that thought, but it's important to work through.
I like that idea. And one thing that came to mind while you were talking about that is thinking of like gradient descent on a potential energy. But there are vector flows that are not gradients of any potential, where you can have, like, if you have circulant behavior, and we know that we have this in preferences, we may even individually have preferences like this, where we like A better than B and B better than C, but we like C better than A, like some kind of circulating preference. There is no way to come up with that as a single reward function that you are optimizing. And so, maybe we need a different mathematical formalism that can account for curl. And I don't know, maybe that's all you need, or maybe you need more ingredients than that. I've never heard of anybody thinking about a kind of curl-based RL system, but that would be a cool thing to explore.
Sorry, what's curl?
Like a curl of a vector field, yeah, like that. Right, the cross product between the del operator across the vector field.
Right. So moving between this kind of local view and the global field. It's
still local. It's still a local operator. It's like the rotational component of a vector field. So you have the inflowing part, which is like the divergence, and you have and then the gradient is the vector part of a potential. And if you take the divergence of a gradient, the curl of a gradient is always 0. So if you have some hill or any kind of topological shape, and you look at the gradient as a vector field, and then you take the curl of that to find if there's any little whirlpools or vortices or rotational flow, it's always 0 for the gradient of a potential. But then there's something called a vector potential, which has non-zero curl. And so that's a more complicated item. And maybe something like that can give you circulating preferences and therefore more complex ways of thinking about what we're trying to do, which is not optimize anymore. It's just, here's the way that we change things.
Right. And maybe something that looks like optimization is in there, but it's not the driving force. It's just another component of what's going on.
Right.
I like that. That's neat. That would be some new math for me. For a while I was thinking about, what do they call it? Blackwell reachability or approachability, Blackwell approachability, which is kind of a different notion of what behavior is trying to do. And it feels more living-y in a sense. It's about trying to get into an equilibrium zone. Right. So there's some kind of happy zone that's defined in the state space, and the operators push you in that space. And the question is, can you actually choose actions to get into the happy zone, as opposed to, can you optimize this quantity, right? Which is the RL view. This is can you become comfortable? And they're related to each other, right? You can make comfort a reward function, or you could define the comfort zone to be, way extreme so that you have to go in a direction to get to it. But a difference, I think, is that you don't just keep pushing, or as Xaq was pointing out on the chat, you don't just keep making paper clips, right? Your goal is to make some paper clips, but not to make all the paper clips. Like, there is no notion. You can't say in Blackwell approachability, just keep making paper clips. No matter how many you've made, that's not enough. There is a notion of enough. And then once you get into the enough zone, it's satisfied, and it tries to keep itself there. It tries to equilibrate. But that's a formalism that's been proposed for making decisions that is different from the RL one. But I don't know where that goes. Right. It still could be problematic. It doesn't fix the problem exactly, but I don't know. But where are these goals coming from? Like, to the extent that the goals are coming from evolution, you'd think that they would be protecting us, right? They'd be at least trying to keep us from offing ourselves before we reproduce. but there's no magic. I mean, there's no must destroy everything that might. Yeah. Okay. All right. So I'll just stop.
That's the problem, that there's always some way around any boundary that we think we put up there. It's intrinsically unstable. If we think that we have the right loss function, there's some way around it. I mean, people see this all the time in monkey training. Like, they never do exactly the way that you want them to do the task. They find some shortcut, and so do neural networks. This is a problem with generalization. They like find some weird pixel in the upper left corner, like a barcode that is correlated with cat versus dog, and then it ignores the picture, or is just like not necessarily focused on the picture and this is a major breakdown mode. Like, we can't anticipate all the things that might be explaining. Do you know about the no free lunch theorem? I'm asking the room. The no free lunch theorem says that there's no way that you're going to be good in any environment. You're always going to specialize to some environment. So you have some bias, which is going to do well here, and it's going to do worse in some other environment. And so they call it the no free lunch theorem. And there are variants of that in a variety of disciplines. So, as hard as we may think about things, the best we can do is focus on like doing well in a narrow, maybe not narrow, but in some range of tasks and worlds. And if you push it far enough, it's going to be worse than doing some random other thing. But I think that it's okay that we live in one world and not another. So we can concentrate our efforts happily there. All right, who wants to go next, Vivian or Michael? Or maybe you can talk at the same time.
I think, Michael, you were first.
Yeah, so this is again, I'm not much of an RL expert. I'm more on the computer vision side and stuff, but I've been thinking a lot about my project my PhD project kind of relates to semantic mapping and how we get from these sort of bottom up trained representations to like conceptual structures and things. And as of lately, so, with the video games, and I've been lately just kind of taking on learning random new things that I never really did and kind of seeing how I learn it and trying to make sense of the process. And I think this kind of relates to both of your talks. So like, I remember, I think one of you had mentioned compressibility at some point. And lately I've been coming back to this notion of compressibility a lot, because when I look at the way I learn things, it seems like I could largely categorize the process as learning that in a particular situation, if I respond in a particular way, things work out pretty well. And then as I get further into learning that thing, I sort of take that rule and I generalize it. And this is where it becomes more of an explainable principle. And so it seems like my process is often something like, okay, very overfit to certain situations, and then learning to connect different situations, and then taking a bunch of rules that are super specific to certain situations and replacing them with a general rule that actually applies in a lot of circumstances. And I kind of see this as largely compressibility. And I'm starting to suspect that largely when we're learning things, what our mind is doing is looking for a more compressed version of the information so that we can throw out a bunch of stuff and kind of replace it with a more general rule. And so, yeah, when I look at I'm surprised that there's not more, I see some emphasis on sparse representations in different aspects of machine learning, but I'm surprised that this isn't more of a central focus and kind of all the way across deep learning. But I think especially in reinforcement learning, it seems like something that would kind of make sense. So yeah, if there's anything you can kind of speak to that with.
Sure. All right. Yeah. Okay. All right. So I should probably try to do better than that. So I think you're exactly right. I think that the phase we're in terms of the deep learning era is one where that hasn't really been the bottleneck yet. But I think we're going to discover that it is, and we have to do a better job of that kind of compressing or that kind of consolidating of knowledge, right? And I do think that it is. You say it's what learning is, but I think it's part of the learning process, right? There's some of the low-level learning and the memorization that's actually part of the learning process. But then as you were describing it, there's a reflection back on what was learned with the hope of having a more general principle and be able to handle a wider variety of situations, and maybe even finding connections between the things you've already memorized, but can capture more succinctly some other way. I mean, that's what science is trying to do. Like, I do think it's a fundamental drive in cognition. And it's right, it's not really, it's only very coarsely in modern deep learning, right? So the notion of regularization has an essence of this, but it's very ham-handed. It's not very subtle or artful.
Well, and that's actually, so what I always found the notion of Kolmogorov complexity pretty interesting. And this is the most, formalized notion of compressibility that I know about. But it seems like in the late 90s, there was some interest in applying Kolmogorov complexity to machine learning applications, but then it kind of died out and hasn't really picked up since the deep learning boom. And I'm kind of wondering if there's a good reason for that. Like, should I not go for checking out Kolmogorov complexity applications because there's something I don't realize about why it's not really tractable or something?
You'd be ahead of, let's just say you'd be ahead of the curve, right? Because I think the problem with Kolmogorov complexity is it's very, it's gnarly. It's a very unhappy kind of search space, or at least unhappy with respect to the way that gradient descent tends to work, right? And so the idea that we could use the tools that have been really successful lately in this other regime is hopeless. It's neural net training and Kolmogorov complexity, I think, aren't friends. And that means that the only way that the field is going to get there is by essentially abandoning or being able to broaden the view away from just TensorFlow or whatever.
Cool. Thank you very much.
We might be running out of time, so maybe should we do Vivian and stop?
Yeah, I mean, I think we're already over time, so if you gotta run, Xaq, then we can stop here. Otherwise, I'd have a general question, maybe for a really short answer. Okay. So yeah, I was just like, after everything we talked about now today, which was, by the way, a really interesting discussion, so thanks a lot. I was just wondering where you judge the current flaws of reinforcement learning. So we obviously see that it's not doing what humans are doing, so it can't really generalize. So do you think it's like more important to work on the algorithm side, moving more toward model-based reinforcement learning, or more important to actually like tweak on the kind of environments that are learned, and like that actually this kind of intelligence that we display is kind of an emergent property of the complex environment in which we learn, and our bodies and actuators, like having hands, opposable thumbs, stuff like that. What your opinion would be on that?
Sorry, I just joined back. I lost my internet, and so I didn't really hear the full question.
Oh no. Yeah, basically just where you see the more promising direction of reinforcement learning, making it more generalizable. So either tweaking on the algorithms, adding model-based parts, etc., or tweaking on the environment with kind of the idea that our intelligence is like an emergent property of the complex environment in which we learn, and the type of tasks we have to solve, and the type of actuators we have to work with, like hands, thumbs.
Gotcha. Yeah, I'm a big fan of embodied computation, that it really matters that we're in a good environment and that we can do multiple tasks and we can explore things with curiosity. But I think that we're really fundamentally missing some things on the algorithm side. I think our learning rules are desperately impoverished. We don't have great ideas for them. We have clever tricks, but they don't work the way that we do. And I don't even know how to make progress in that domain. But those are things where we have a very strong inductive bias, which means, so a model bias is a bias in the mapping from input to output. An inductive bias is a bias in the mapping from a data set to model parameters. So it's basically, what do you learn? And the inductive bias that we have, which is much better, like much faster at generalizing, extracting abstract concepts, all of this, much better than machine learning, comes about by a combination of lots of factors, which is like our brain architecture at the large scale, maybe the microcircuit at the small scale, the learning rules at the tiniest scale, and then the way in which we interact socially with other things that are teaching us, like the curriculum learning and all of that. So I think that we really need some fundamental changes in the way that we train our agents. And we can get by for now without doing that because we just crank up the compute power. But at some point, the problem complexity gets big enough that we don't have enough compute power to do that. Like these architecture searches that people are doing, they take up as much energy as a lifetime of 5 cars traveling, like building them, driving them all, just to, you know, the energy consumption and the amount of data that you have to consume in order to do that. That is not the way that we work. I mean, yes, we have a head start because evolution has gifted us our inheritance of a good inductive bias, but we would like to learn that inductive bias and import that into a smarter learning agent.
That seems awesome.
All right. Yeah, thanks a lot. So I think we're already over time. So if everyone is okay with this, maybe we finish this panel discussion here. Thanks a lot for both of you for being here and everyone else for being here and asking questions. And hope to see you around.
Thank you, Ashima and Vivian, and anybody else who was involved in organizing. This was really fun. And Michael, nice to have a chat with you. It was really entertaining, and
Yeah.
I look forward to the next time.
Awesome. Thank you. Bye,
Thank
everybody.
you.